All right, here we are continuing on with our Chapter 12 videos. And our previous video, we were talking about dispersion forces, how they are the weakest of the intermolecular forces, but everybody can do them, so they're probably the most ubiquitous. Our next strongest is the dipole-dipole force. And in order to have dipole-dipole forces, you must have a polar molecule. Right? So the ability to tell whether or not a molecule is polar is going to be very important here. Now, contrary to the dispersion forces, dipole-dipole forces are a permanent attraction. Right? Remember, our dispersion forces was all about the movements of electron clouds and polarizing electron clouds. So it was constantly shifting, right? With dipole-dipole forces, we have permanent dipoles because we have polar molecules. And so if I have a pair of molecules here, right, if we have a permanent positive and negative end to our molecule because it's polar. So I'm going to have attraction between that positive and negative end that is permanent, which makes it stronger than the dispersion forces. So if I look at the difference between dispersion forces and dipole-dipole forces, so if I have a nitrogen molecule, right, it's nonpolar, so all I can do is dispersion. Right? And if I have another nitrogen molecule nearby, we get a shift in our electron cloud, and maybe we get a little bit of interaction between the two. Our boiling point for the nitrogen is a mere 77 degrees Kelvin. Now, on the contrary, if I move just one atom over on the periodic table, and if I have my nitrogen monoxide, this one is a polar molecule in favor of the oxygen. Right, so I can have dipole-dipole. Right, so I've got a negative end and a positive end, a negative end and a positive end. So I'm going to have a fairly good permanent attraction between those two ends. The boiling point for nitrogen monoxide is 121 degrees Kelvin. Right? So stronger forces result in a number of things. We'll get higher boiling points, right? Because stronger forces will oppose vaporization. The molecules will hold on to each other longer and tighter and require more energy in order to cause, before they will allow molecules to go into the gas phase. We'll get higher melting points. We'll get higher surface tension. We'll get higher viscosity. Okay, all these things are influenced by the strength of intermolecular forces. So polar molecules can do dipole-dipole forces. All right, so let's take a look at some examples of how dispersion forces rank up against polarity and see if we can see a trend. So I've got a few molecules here that will have the same structures. The only differences are they are in the same family of the periodic table, but one away from each other. So I'll have as my first guest H2 tellurium, then H2 selenium, H2 sulfur, and H2 oxygen. Right, so we've got molar masses, 129 AMU, 81 AMU, 34 AMU, 18 AMU. Right, so we can already see that dispersion strength will favor the heavier molar mass. Right, so let's take a look at structures. So they're all the same structure because they all have the same number of valence electrons. They'll all be bent with 2 electrons, 2 lone pairs on the central atom. Right, so no difference in structure, no difference in bond angles, anything like that. So let's take a look at polarity. So with my tellurium, there is no electronegativity difference, so delta En for electronegativity, between the tellurium and the hydrogen, so we are nonpolar. Right, with selenium, we have a little bit of polarity, 0.3. So we're a little bit polar towards the selenium. With the sulfur, we have just a little bit more, 0.4. So again, slightly polar. And with our oxygen, oxygen is far more electronegative, so we have a much bigger polarity difference. All right, great. So oxygen is the only truly polar molecule here, but the tellurium compound has the much higher molar mass and stronger dispersion. So let's take a look at our boiling points for these compounds. And so BPs. So for the tellurium, we have minus 2.2 Celsius. And then with the selenium, we're still basically more or less nonpolar, so we're depending on dispersion forces. So weaker dispersion, we should have a lower boiling point, and we do. Minus 41 Celsius. Same thing here with the sulfur compound. We're still mostly nonpolar, so we depend on dispersion. So we're minus 60 degrees Celsius. Right, and then we hit water, which is a polar molecule, so that's going to have a much stronger force than the dispersion. So our boiling point should go up. But surprisingly, it goes way up. So the boiling point of water, we all know, is 100 degrees Celsius. Right, so polarity doesn't fully account for that much of a difference. For a change in 160 degrees to get all the way up to the boiling point of water, polarity doesn't quite cut it. Right? So the only way that we have to explain it is with our third type of intermolecular force, and that is hydrogen bonding. Okay, and of the 3 main types of intermolecular forces, hydrogen bonding is the strongest. Now, in order to have hydrogen bonding, we must have hydrogen bonded directly to oxygen, nitrogen, or fluorine. Right? Can't just be in the same compound, but the hydrogen has to be actually connected to one of those elements. Now, there's an important distinction between a hydrogen bond and the intermolecular force of hydrogen bonding. Right, so let's take a look at water for our example. And well, let's say I have another water molecule nearby. Whoops. Right, so when I'm talking about hydrogen bonding, I'm not talking about these bonds. right? Yes, it is a bond to a hydrogen, right? But hydrogen bonding specifically is the interaction between the two molecules. Right, so if I have another water molecule nearby, we'll have an interaction between the molecules. Oops. Make sure you have the right colors for everything. Gonna make our drawings come out pretty. Right, now each oxygen can take two bonds, two hydrogen bonds, and because I have two hydrogens on each atom, or each molecule, I can then donate two hydrogen bonds. And donate two. Okay, because each oxygen has a pair of lone pairs, two lone pairs on each one. So we're able to accept the interaction of two hydrogens. Right, now hydrogen bonding is directly responsible for life on this planet. It's the reason that ice floats. So most materials, when they go from a liquid to a solid state, the molecules get closer together. And your solid ends up being more dense than your liquid and sinks. Okay? Hydrogen bonding keeps the space between the oxygen molecules as it solidifies. So the result is that our ice is less dense than water and floats. Now let's take a look at comparing relative strength of different molecules that can hydrogen bond. So if I have a trio of molecules, and imagine that we have hydrogens on the end of each one of these little lines, and the second one looks like and our third one all right, so predict which of these will have the higher boiling point. So let's take a look at what we have to work with. So our top one has two carbons and the ability to do hydrogen bonding from one site. Our second molecule also has two carbons, but we have the ability to do hydrogen bonding from two locations. We also have a bigger molar mass with the addition of that extra OH group. And then our third, we have three locations for hydrogen bonding, and we have three carbons instead of two, so a much bigger molar mass. All right, so all of them can do dispersion, all of them can do hydrogen bonding. All right, so the one with the ability to do the greater dispersion and the most hydrogen bonding will win. So if I have boiling points for each of these, my first compound will have a boiling point of minus 114 degrees Celsius. My second one in line will be minus 13 degrees Celsius. And my big one with the three hydrogen bonding sites, 17 degrees Celsius. Right, so stronger forces, higher boiling point. And we're going to go ahead and stop this video right here, and we'll pick it up on the next video and talk about what happens when we introduce ions into this situation.